Today I'm going to be talking to you about a new discovery made by scientists that looks to harness the carbon dioxide already in our atmosphere to develop new biofuels. As we learned in class, enzymes and catalysts are capable of lowering the activation energy needed to drive a reaction forward. Since carbon dioxide is not generally very reactive, researchers needed to find a catalyst to force the reaction to progress more easily. Two sets of researchers discovered two different ways to essentially imitate the photosynthesis process using light as the main energy source. The first method, proposed by researchers from the University of Illinois at Chicago, converts carbon dioxide into carbon monoxide, which is much more reactive. And then the carbon monoxide can be further processed into a useful fuel product. The second method was discovered by researchers from Utah State University, and they developed a process to convert carbon dioxide into methane in one singular step using a biocatalyst. As I previously mentioned, the first method for converting carbon dioxide into a useful biofuel product was by breaking the carbon dioxide molecules down into carbon monoxide molecules. This is important due to the fact that carbon dioxide is not very reactive, while carbon monoxide is much more reactive and much easier to further process. Researchers were able to carry out this reaction using a metal catalyst called tungsten diselenide. Since there's no real substitute for a natural enzyme though, researchers were forced to grind this metal compound up into small flakes that increased its surface area and its reactivity. The process used here was actually a three-step process, for which the researchers designed an artificial leaf that was capable of carrying out this entire process. Once the carbon monoxide was formed, researchers were able to use processes that have been in place for years to turn the carbon monoxide into something useful, such as methanol. Although the reaction required 3 steps, the researchers found that it was actually pretty efficient in terms of its energy return on investment, and that the tungsten catalyst used could also last for as much as 100 hours. Method number 2 utilizes a process that is capable of turning carbon dioxide in the atmosphere directly into very useful methane gas. The researchers from Utah State were able to harness a biocatalyst, which is also known as an enzyme, to develop a one-step process that converts carbon dioxide into one of the most widely used fuels in the world today. The enzyme is known as Rhodopseudomonas palustris, and it is a phototropic bacteria which uses light as its main energy source, very similar to photosynthesis and a leaf. This process closely resembles photosynthesis that plants use to create sugars from sunlight and CO2. Again, the use of this enzyme dramatically decreases the activation energy needed to reduce carbon dioxide into a useful reactive compound. In this case, researchers were able to develop a process that only took one enzymatic step and was able to directly create methane from carbon dioxide. There's a long list of benefits associated with this process and its product fuels. For one, these fuels are highly renewable due to the abundance of carbon dioxide in our atmosphere today. If this process were to be scaled up and used globally, it's completely possible that we remove vast amounts of carbon dioxide from our atmosphere, which would be a positive step in reversing global warming trends. In addition, these fuels would create a sort of cycle where carbon dioxide is removed from the atmosphere to make fuels, as much as these fuels are burned to create more carbon dioxide in our atmosphere. As an added bonus, researchers believe that these processes can be used to make other useful products and materials as well. While there are many potential benefits, there are also quite a few challenges and questions this technology must face. For starters, how easy would it be to capture these vast amounts of carbon dioxide and harness them to make a fuel? In terms of producing these fuels on a large industrial scale, would it be easy to just build a chemical plant and carry out this process? Is there enough light energy to carry out this process on such a large scale? Are the catalysts used in this process potentially harmful to the environment? How would they be disposed of after their useful life? Could they be recycled? Lastly, would there be any difference between these product fuels and the conventional fuels that they resemble? Is it possible that the physical properties of these fuels could differ? Would they have any differences in their combustion processes? These are questions that must be answered before we scale up these technologies and use them on such a large scale.